All right. Controllability and observability. So these are two very important concepts in modern control systems. In fact, in 70s, um, the, the whole system um, underwent a major change in the way we used to look at control systems, right? Pioneered by Richard Kalman, and the modern control systems based on time domain analysis, state variables, right, state feedback, and of course, controllability and observability. All these concepts actually revolutionize the control system field. So these two techniques, these two concepts play a huge role in modern control systems. So let's look at what they are. Now, first to controllability. So what is controllability? So if you just read a paragraph on controllability, it will tell this. A system is controllable, right? System means a plant, right? Is controllable if the state could be transferred from an initial state to a desired state, right? You have initial state, you have desired state, right? By means of an unconstrained signal in a finite interval, right? So the time is finite and the control signal is unbound, right? Or unconstrained. You can get any big control signal as you wish, right? Positive or negative. So there's no bound, there's no controller saturation kind of problems, right? If it is the case, right, you can move the plant from initial state to any final state within that time period. That is if the system is controllable. So now the problem is, how do we know whether this is controllable, right? So for that, the requirement is this. This is a check whether all the states are affected by the control input. There you are. Now, if you look at a plant, it has a set of state variables, right? X1, X2, up to Xn. And if you write down these equations, and if you can figure out that some sort of relationship is there between control signal and any of these state variables, and all of the state variables actually, right? Then we know, okay, we can use the control signal, right, to drive each and every state variable from initial state to the final state. So that is what we are trying to figure out here, controllability. And on the other hand, if we know that some of the state variables they're not related to control signal in any way, then of course we know that we have no control over those state variables. So therefore we cannot provide any assurance whether we can bring the state variables, those state variables, to the final state. Okay. So this is the check we are trying to do under controllability, to see is there any relationship between the state variables and the control signal. So each and every state variable, okay, is related to the control signal. If it is the case, system is controllable. If it is not the case, those state variables are not controllable. So if you have a number of states in your plant, right, and just one of them, at least one of them, is not related to control signal, then we say the whole system is not controllable, right? For a plant to be controllable, not only n-1 state variables, but all n variables are supposed to be related to the control signal. So that's how it works, okay? Right. So I have illustrated the state transition from x0 to xt. Now you know this state transition. We have worked it earlier. So you should be in a much favorable mindset to understand the controllability and observability. So the plant is moving from x0 to xt. Plant is moving from x0 to xt, right? Under the influence of some control signal, right? And we want to find out whether this control signal is actually related to all of the state variables. So let's see how we can do that. Now, below here is the state transition equation with control signal, right? UT. Now, without losing generality, we can set xt equals 0. Now, I think that's not a surprise to you to set the final destination of the system to be 0, right? So when you do that, on the left-hand side is 0. You have e to the at x0 plus this convolution integral. And you isolate x0 on the left-hand side, initial state, and it will be like this. E to the at will go to the other side as e to the minus at, right? So what is this? On the left-hand side is the initial condition. So wherever you have your system initially, right, it's not 0, and you want to drive to 0, right? Generically, this is the control process, right? When you have a disturbance, you want to quickly recover from the disturbance and come back to 0. 0 is the default position, right, for regulators. Right. Now, if you remember the Cayley-Hamilton, there it says e to the minus a tau, right? You can write this as a summation. So what is that? It's a summation from k0 to n minus 1, right? Alpha k tau ak, right? You have the system matrix A using that one, not in the exponent, right? But as a general matrix raised to the power k, and you have some alphas in front of that, right? So if you use Cayley-Hamilton onto this equation, right, you can replace this e to the minus at, right, and putting a summation, right? And then you can take the summation out and put the integral into that one, and you can write it like that. Summation from 0 to n minus 1, a to the k b integration 0 to t alpha k tau u tau d tau. Okay. Now, this is a matrix multiplication actually. All of these terms, right? All of these terms, n terms actually, right? Because this n dimension n system, n state variables, right? On the right hand side is n terms in that format. So you can see AKB from k from 0 to n minus 1, right? This is the entire matrix there, B, A, B up to A n minus 1B. And for each term, there is another counterpart here, integration, 0 to t, alpha k, tau, u tau, d tau, right? So for each k, you work out this one and put it over here, and the integral part is over here. Second term, AB here, and the integration is over here. Likewise, you break it into two vectors, row and column. Okay. But these are all matrices. So when you multiply, eventually you get this vector, not a scalar. Okay. Now, if you just treat this entire column over here, this is integration. u tau, alpha tau, u tau, d tau, right? Integration. This is a scalar, right? And all these terms are scalars. Once you integrate, it's a vector, okay? Just a single vector. Now, what in front of that is a matrix. It's a matrix, and we call it controllability matrix. Controllability matrix. So now the problem is bit very clear actually here, because on the left hand side you have x0. X0 is a known thing. It is the initial disturbance or deflection of the plant from 0. Right? If it is a second order system, you are supposed to be at 0, 0. Position 0, velocity 0. Right? Then you are deflected to a different position with different velocity. Right? It's like a pendulum at 0, 0, and you deflect it a little bit. And after that, it comes back and gradually settle down and reach the equilibrium position after some time. Okay. So this initial deflection is a vector in tuples, right? x1, x2 up to xn. On the right hand side, you have the same vector over here, but in between there's a matrix. Now, if you are to have a solution for this simultaneous system of equations, right, it's very clear that this matrix should be non-singular, okay? And it has to be full rank matrix. In other words, what it says is that if you look at the rows of this matrix, right, the rows should be linearly independent, which means there should not be any row in that matrix which is a linear combination of other two or many rows. Say, for example, if you have the first row 1, 1, 1, second row 2, 2, 2, obviously they are linearly dependent, because if you get the first row multiplied by 2, you get the second row. They are linearly independent. They are not independent rows. They are linearly dependent, right? So in that case, we call the matrix is not singular, right? And it's not full rank in that case. So full rank matrices, they are rows. If you work out in rows, they're all independent rows, right? They're not linearly dependent. If you work column wise, you can say the same thing. So if the C matrix is full rank, system is controllable, which means there is a unique solution for the control signals, right? To work out starting from any deflection, any arbitrary x0, right? You can bring that to 0 in finite time. Okay, and this is the control signal. You can find this u tau. What is this continuous control signal, right? Which will bring x1, x2, x3 up to xn, all of these initial states to 0. So the requirement is the C matrix or controllability matrix be full rank. A very simple test in MATLAB. The moment you know A and B, you know this. The moment you know A and B in MATLAB is a single command. It will give you the rank of C matrix, and you judge if it is full rank, right? System is controllable. Example. So look at this one. Is a second order plant x1 dot x2 dot, and this is the system matrix 1, 1, 0, minus 1, and this is the drive matrix 1, 0, u. And you want to check whether the system is controllable, which means whether the u, the control signal, is related to x1 and x2, right? So Now you know what you're supposed to do. You get the controllability matrix C, which is in this case B and AB. B is the first column, AB is the second column. So B is 1, 0, you write it over here. Second column is AB, multiply A and B, right? Then you get 1, 0 again. This is a singular matrix because you know first row and second row are linearly dependent. So if you take first row and add to it the second row, you get the first row back. So they are dependent, right? So your conclusion is the rank of C is less than 2. It has only one linearly independent row, this or that. The other one is linearly dependent. The controllability matrix is not full rank. It's not full rank. System is not controllable. Okay. Any questions, please? Is the controllability as a concept very clear? And is the process how you check controllability of a plant is also clear? Any questions, please? So let me check with some of you guys. Dhananjay, is that clear to you?
Yes, sir. It's clear. Yeah.
Okay. Then Tilanka? Tilanka, is it clear to you?
Yes, sir. Can you hear me, sir?
Yeah. Right.
Yes, sir. It is clear, sir.
All right. Then Vitanasiri.
Yes, sir, it is clear, sir.
Right. So it's a simple technique using the two matrices A and B. You put it to this format, right? If the resulting matrix is full rank, system is controllable. So this is how you do it in MATLAB. C is equal CTRBAB. That's it. Okay, and then check the rank. There's another example here. We have another second order system, different system metrics, same dry matrix. Okay, so now the controllability matrix is again this one, BAB, but the first row is 0, 1 here, and the second row 1, -1. Well, this is a non-singular matrix. If you look at the first row and second row, they are not dependent on each other, right? They are not linearly dependent. They are linearly independent. So therefore, the rank of the matrix is 2. It's a full rank matrix. So therefore, the system is controllable. Let's check another one. What about this? It's another second order system, but different system matrix. Oops. Oh. Yeah. This is in fact the first system again. This is not a completely different system. This one up there, 1, 1, 0, -1, this matrix, right, is the same here. So we are going to look at the system bit more clearly now, right? Not just applying this controllability matrix, and if it is not full rank, it's not controllable. If it is full rank, it is controllable. Now let's look at, let us dissect the problem and see why it is not controllable, right? So this is what we had earlier. Controllability matrix is singular, it's not controllable. Now, if you expand this set of equations, right? In fact, the state space model is set of equations put together in a matrix format. Now, if you write down the first equation, it is x1 dot equals x1 plus u. Then second equation, x2 dot equals minus x2. This one. So, there are two equations. Now, without any assistance, you can take it up and comment whether it is controllable. Now, if you look at the first one, what do you see? What can you tell me about the first equation? Where it says the rate of change of first state variable is equal to the first state variable itself plus u. The moment you see that equation, what is your conclusion? Is it stable or unstable? Is it stable or unstable? Can somebody tell me? It's a very simple question. What do you mean by stable and unstable? If you look at this equation, what you see, the rate of change of something, right? Let's say it is the price of a loaf of bread. Okay, this is the rate of change of the price is equal to this is the price. So what's going to happen to the price if it changes like that? The rate of change of the price of bread is equal to the price of bread. Forget about you. What will happen to the price gradually? If you work out this equation every day, after about a week, a month, what will happen? Sri Lanka, can you answer that question? Vihangi? No one can answer? Yasiru?
Still increasing day by.
Yeah. Chamira?
Increasing.
So I don't know why you guys cannot answer me quickly. Why I had to take a lot of time and effort to get this simple answer. So don't waste our time, right? Quickly answer when there's a very simple question. If it's a hard question, that's fine. But this is such a simple question, right? I don't have to put you these examples like loaf of bread and all that. You are postgraduate students, right? Quickly give me answers. Now, if you look at that one, this is rate of change of something, which is equal to the value of that thing, right? This is positive feedback, right? You are not studying control systems for the first time, right? And you are at the postgraduate level now, right? These are very, very simple questions. Anybody would answer. Even a O-level student will answer that question if I ask. So rate of change is very key, right? Rate of change of anything is key. Look at that, where it is going up or down, right? And who decides that? And this time, the variable itself. So if it's a positive variable, rate of change is also positive. So which means it goes further and further and further and further. If it is negative, it goes the other way. So it goes this way or that way. The system is unstable. Pretty simple. Okay. So if the system is to be stable, then what should be the relationship? Natural relationship. Like if you look at our body, blood sugar, pressure, and other things, right? They are naturally regulated. So what happens there? If the blood pressure increases, there's a system in the body to reduce it. To reduce it, rate of change should be negative. If the value is positive, rate of change has to be negative, exact opposite. And that is why we do negative feedback in feedback controls, right? Not positive feedback. You always negative feedback. That is the very reason. If you want to stabilize, it has to be negative feedback, right? Okay, fine. So therefore, the first one is not stable, but there is U there. Control signal is there. So we can do something, even though the relationship is unstable, right? You can intervene and try to stabilize it. Like, for example, the government intervenes with price of egg, loaf of bread, price, whatever. And if you just let it float, U is not there. And this will go and settle wherever it finds some sort of peace. And at that time, it will be unbearable for people, right? Not affordable. So therefore, government intervenes and fix it. So this is exactly what's happening there, right? So therefore, even though the relationship between x1 dot and x1 is unstable, right? Because U is there, it's controllable. That is the story of the first state variable. What about the second state variable, where the relationship is this? Rate of change is equal to minus x2. There, it is exactly what we expect to see, right? Value of the state variable, right? And the sign is negative, opposite, and that is the rate of change. So if we apply this to loaf of bread, what will happen? If it is high price and rate of change is negative, so it comes down. It doesn't continue to rise, okay? And also if it goes below a certain level, right? Don't think about zero, some reference value. If it goes below that, it will drive it up, okay? So it finds some stable point. So it is naturally stabilized. But do you see any control signal over here? No. Second state variable is not related to control signal, right? So we cannot control it, but it controls itself. Therefore, it is stable. So second state variable is stable, but not controllable. Whereas the first state variable is unstable, but it's controllable. Now, this is a very nice setup here for you to understand how the state variables change, how the control signal is connected to these state variables, right? You can see much more details, right, of the control system down to the state variable level, how each and every state variable changes. All right, is everything clear now?
Yes, sir.
So if you want to write down the two state equations, x1 dot and x2 dot, it will look like this. So this is the first part, controllable part, controllable but unstable part. And this one is uncontrollable but stable part, okay? Right. So that's it for controllability. Now let's look at observability. So what is observability? So the simple answer is just few lines. You can see it over here. A system is completely observable if the state xt can be determined from the observation, that is yt, over a finite time. Right. Now, the system here is the set of state variables. I think you know that, right? State variable vector. If it is an n variable system, there is n state variables. If you know the value of each state variable, you know the system. You measured the system. But if you do not know state variables, it's not observable. Now, how do we know about state variables? So you can say we put sensors and measure all of them. But here it's not the case. You can put sensor and measure anything, then it's entirely, you are actually modifying the plant and then get the signals, whatever you want. But when you develop the theory, right, we assume that you measure some signals, not everything, right? Not every state variable, maybe one, maybe two, like that. So now we are trying this. We have a few state variables measured. Other state variables are not measured. And we are trying to figure out whether these measured variables for some time, right? If you keep taking readings of the response, right? Maybe just one state variable. Can you estimate the other state variables? If you can estimate the other state variables using whatever variable you measured, then the system is observable. So it's the literal meaning of the word observability. Okay. You are able to estimate or calculate state variables from what you have measured. So if the system provides you a mechanism for that, if the system is so nicely connected that way, all these relationships are there, so that the state variable information is embedded in whatever state variables you measure, so that you can back calculate and estimate the unmeasured state variables, we call the system is observable. Is that conceptually clear? Any questions about that? Observability?
Yes, sir.
Anybody who is not very clear about observability? I think it's clear, right? Okay, so here is the mathematics related to observability. We start with the system x dot equals ax, y equals cx, right? Let's neglect bu, control signal here, because if the system is observable, right, it is observable even without the control signal. And if the system is observable, it's not going to be affected by the control system when you put control system in, right? Your observability, which is already there, is not affected. So therefore, you can easily take, conveniently take the control signal out of the plant and develop your theory on observability, right? So for that reason, we only take the homogeneous part of the system, x dot equals ax. So if you look at observation, now we keep observing some of the state variables, not everything, right? So yt is equal to cxt. This is the observation or measurement. Then y dot, if you differentiate that one, it becomes cx dot. So by the way, when you measure your state variables, right, we assume that you collect the information about the rate of change also, right? How the output changes, y dot, y double dot, and so on, right? So that information is already available. So any combination of whatever you have measured is also information available, right? You can make use of all these. In fact, in here we use successive differentials, right? Derivatives of yt as available information. So we have y dot, which is equal to cx dot. Now x dot is equal to ax. It is a system equation. X dot equals ax. So that you can write down this as c times, in place of x dot, you can write ax, right? So eventually it is cax. Whereas the first one is just cx. So you keep writing y double dot t is equal to what? Then it will be c what? C double dot x, right? So then you put two of them together, it will be a square. So like that, it keeps growing the variable here. So this is the first x dot, x double dot, like that, it'll increase. So when you substitute from the system equation, which is x dot equals ax, you eventually generate this one. So eventually for y n minus 1 t, right, n minus 1 t, that is n minus 1 derivative is equal to c a n minus 1 xt. Now you put them into this matrix equation, right? On the left hand side, it is yt, the direct measurement, and all its successive derivatives up to n minus 1. So they are all here. And on the right hand side, you have this matrix C, CA, CA, n minus 1, all these matrices. And after that, it is just xt. All of these equations will have xt. So xt is an n-tuple, right? All of the state variables at time t, initial deflection, right? Same story as we discussed earlier, initial deflection. And on the left-hand side, it is the measurement, right? Yt and all of its derivatives up to n minus 1. So if you want to find out a unique solution here, right? For any xt, any deflection initially, right? For the plant to go back to 0, right? Then this matrix in between, Cm minus m times n, Ca m times n, they are all m by n matrices. They're all m by n matrices, right? And this has to be full rank. This has to be full rank. Okay. So if it is full rank, which means there is a unique solution. There's a unique solution. And the system is completely observable. Is that clear? So this is actually the state variable vector. State variable vector. And you have no idea, right, where the values are. But this equation tells you if you keep recording these ones, right? If you have yt, y dot t up to yn minus 1 t, all of these values, if they are available, and if you have this matrix also, you can calculate xt. Very simple. For that, what you need is that this matrix is invertible, because you can bring this to the left-hand side as inverse. Right? If the matrix is non-singular, is not invertible, then you can't do this. This has to be invertible. For a matrix to be invertible, right, it got to be full rank. So is it clear now? Maybe this is bit confusing than the controllability. Is about estimating this vector xt. We want to estimate xt. Xt is all the state variables, x1, x2 up to xn. And we don't have sensors to measure all of them. But what we have is this one, y dot, and all successive derivatives. So you have successive derivatives of y, your measurement, and also this matrix in between, which is inverted here, and you pre-multiply yt with that matrix, which is inverse of this one. The result is xt. All of the state variables are there. Okay.
So the matrix should be non-singular or singular?
Non-singular.
Non-singular.
Non-singular. Only non-singular matrices can be inverted.
Yes. For the
Then you can, yeah, when you bring it to the left-hand side, is the inverse, right? So it should be invertible. In other words, non-singular. In other words, full rank. Okay, so all these names say the same thing. All right. Any questions? There's a question here. If the system is uncontrollable, then do we need to consider about its observability? Well, these are two concepts. These are two concepts. Sometimes we combine them together when we design controllers and all. But there are two concepts. Now, maybe you asked this question before we finish this discussion. So if you look at these two concepts separately, right, if you take this one first, what it says is that you have a sensor, you measure the response, and you calculate the derivatives of that response, and you have another matrix, right? Then you calculate what is the state of the plant, x1, x2, x3, all the state variables, using just one sensor. That's one thing, okay? And on the other hand, you have the control signal, not the response, control signal, right? And you check whether the control signal actually related to all of the state variables, x1, x2, x3, x4, x5, like that, right? If it is the case, your system is controllable, and you, using the control signal, can manipulate all of the state variables, can affect all of the state variables. You can drive state variables, okay? That is a different concept. Now, let's say there's a system which is not controllable, and some state variables are not controllable, right? And maybe they are stable naturally. So they hang on at some point, right? Some values, and we have no control over it. Other variables we try to control, right? So whatever it is, there is set of state values, right? So the system is not controllable, but the system has, it's a dynamic system. It has some values, right? Whether you can control or not, system changes its own. So there are values, state variables. And if the system is observable, you can use that sensor and observe your response and get the successive derivatives and calculate the state. What is the value of the state? Otherwise, you never know what the value of the state is, right? All the states. So there can be systems which are observable, but not controllable. And also controllable, but not observable. You can control all the state variables, right? But you can't see them. You can't estimate them. And all of these combinations are there. Is that clear? Any questions, please? I think this is very, very important concept in modern controls. All right. So it's not very easy to understand, I know. So that's why I prepare all these things to help you understand. So spend a little amount of time to revise it. But when you practice it, it's so easy. In MATLAB, it's just a single command. Like for observability, it's just this much. Observability matrix, you can calculate using this command, obsv, and the two arguments, A and C, right? And then check the rank. If it is full rank, system is observable. Right? So this example, 1, 1, -2, -1, x1, x2, 0, 1, u, y equals 1, 0, x1, x2, the state vector. So this is the C matrix. So actually you are measuring only one variable, x1. You are not measuring x2. But we want to find out whether we need the additional sensor to calculate, to estimate, measure x2, or whether we can estimate x2 from x1. Now, think, for example, if you have a fifth order system, and if the system is fully observable, you need just one sensor, right, to measure whatever that state variable, and then calculate all the other state variables, right? So you don't need any additional sensors in the plant, right? If you do not make use of this observability feature of the plant, you would probably say, okay, we need 5 sensors for the plant. Sensor 1 to measure state 1, sensor 2 to measure state 2, like that. But that is quite unnecessary. You can cut down all these sensors and bring in observability concept and figure out a different controller based on the observer. And we call it observer-based control. This is a separate area in control systems, observer-based controls. Okay. So that will help you get a good result, good performance, and in the same time to get rid of some of these sensors. The sensors are expensive, right? And you make the system complicated with more sensors. So this particular one, if you take the observability matrix C and CA, first row is C, second row CA, 1, 0, 1, 1. So this is full rank. So therefore system is observable. You don't need a second sensor. You need just one, and you can estimate the other state variable. So naturally, we are landing on this topic now. With the knowledge of the observability and controllability, we can take up the observer design. Right? Already you know, I just explained what is it. It's before this discussion, right? Before we discuss about controllability, observability, we learn about state feedback. You remember that, right? State feedback. What was it? You take all the state variables, multiply with a set of gains, and feedback. So when you do that, you figure that out, you need to have all of the state variables available for you to implement full state feedback. So let us call it full state feedback. right? You need all of the state variables to do that. So at that time, we did not ask that question, whether we really have all these state variables available for measurement, right? We did not ask that question. We took it for granted. We assumed all the state variables are available, and you just need to multiply them with gains and feedback. But now we question, right, whether or not all these variables are actually available for measurement, and the answer is no, not quite, right? You may have some of the state variables available, make use of them, but there are other state variables that are not measurable or too expensive to put a sensor to measure those variables. So now we know additional stuff, that is observability, which says you don't actually need a lot of sensors. If you measure some of the sensor state variables, you can actually estimate other state variables. So let's make use of that concept and try to develop a block, an entity, which is called the observer, which will estimate or predict the other state variables that are not measured. And then we will combine all these state variables, measured ones, estimated ones, together and feedback and implement full state feedback. So that is the plan. Okay, right. So let's take a look at some of these basic highlights here. Sometimes not all states are available for measurement, right? You know that. Maybe it is not practical to measure, or too expensive, right, to measure all states. So we want to get rid of some of these sensors that can be placed by the observer, right? Observer or estimator is another dynamical system made by RLC components. Okay, this is a block which is made of RLC components, right, to produce essential state variables. Now let's look at the diagram. This is the observer-based control system. Okay. You have here plant, right? That is x dot equals ax plus bu. This is a state space model of the plant, right? So you need u for that. That is a control signal which is coming over here, right? So it produces x dot as the output, where once you integrate it, it goes as x, actual x. And then you have sensors to measure some of these state variables as y. So not every state variable here comes out of that. So some variables are measured, some are not. So the unmeasured states are inside the plant and nobody knows the values. What you know is only these values, y. Okay, so that's the plan. Now we bring in another electronic circuit, we call it observer, using RLC components. It runs this algorithm, right? The observer. So what it does is that the same plant, you know A, you know B, right? You know, assuming some of the state variables you have estimated. Let's assume you have estimated, right? Not measured, estimated. Then you can put all these x hats and all that. You can run this algorithm. And also what you do is that this algorithm produces an output which is very similar to this plant. And once you integrate, it becomes x hat. Hat means estimates, okay? Not the actual values. The estimate of that value is labeled with the head. The moment you see the head, you understand that this is the estimated variable, right? The estimate. And then once you send it through C, the output matrix, you get Y hat. Now you have two different systems, actual system and the observer, operating in parallel, taking the same control signal U, right? But there's a slight difference between the two systems over here. So the output that is produced by the observer, that is Y hat, we compare it with the actual output Y, and we take the difference EY, right? And we multiply it with the gain K0 and put it over here, right? K0 times EY. So we create this observer plant, right? Taking the system information A, B, and also this clamping mechanism. This is a clamping mechanism to make sure that X hat dot will stay very close to X dot, right? Because otherwise, if you have two independent systems, they are working in tandem, in parallel, but totally independently. There's no relationship between these two. But when you couple them here like that, right? Y and Y hat, right? So Y hat will try to reach Y. This guy will try to reach Y as quickly as possible. So that's why, right, you have this block here. To make sure your observer plant is actually linked to follow, you make the observer plant to follow the plant. Otherwise, there's no point now. You have to make your observer has a natural tendency to follow the plant. So how can you do that? By this type of mechanisms, right? You produce some output and compare it with Y, and any difference you can bring it over here and affect X dot hat. So this natural feedback, right, will make sure that the observer has a tendency to follow plant. When the plant changes, the observer also changes and stay very close to each other. So you have here K0, some gains, and you can make sure these gains are very strong so that the observer follows the plant very quickly, fast. Okay. If there's any difference, quickly the gap will be cleared, and observer will track very closely the plant dynamics. So if it is the case, this X hat, so when Y hat is equal to Y, X hat is equal to X, right? So when this happens, X hat will be equal to X. So even if you do not have X, if you do not know X, you still have X hat. And knowing that they are equal or very close to each other, you can use X hat for feedback. All the state variables are here, not only just one or two. These are the measured ones, but all of the state variables are estimated here. You can use that as feedback. See that? This is the estimated states. You feed it back and multiply with minus K and over here. So we are implementing the full state feedback using the state estimates, not the actual states. So whether this is right or wrong is a question mark. You can argue. how accurate is it to use estimates, not the actual state variables, for feedback? And you can argue, you can say that the observer gains, this K0, are very high, so that if there is a difference between y hat and y, it will be quickly reduced, this error. So when y hat and y are equal, x hat is equal to x, right? So therefore, it's okay to feedback state variable estimate in place of actual state values. Is that clear? Any questions, please?
So,
Yes,
can
go
you
ahead.
use the observer can be in a microcontroller like thing, or is it RLC circuit always?
It has to be, because it has to be very fast. So if you implement it in a microcontroller, you have to get the hardware signals through analog to digital converters into the microcontroller, right? And then apply your software, right? And that will cause a lot of delays in the plant. So therefore, this is just one type of thing, right? A is a constant, B is a constant. They are not changing all the time. So you can implement this on hardware. It's only hardware that provides you fast convergence, because this loop operates very fast. You can see it over here, right? This loop, this happens very fast. The control loop, which is here, you take X hat and like that, this big plant, this big loop, right, happens relatively slowly. So let me draw it. Yeah, so this part, this feedback, taking Y hat, right, and feeding it back, right, and producing Y, right, producing Y. Let's say this is happening 10 hertz, 10 hertz, right? Then over here, you have this loop. Y hat goes over here and comes over here and go into that one and produce X hat, right? This loop works in probably 100 hertz or more, right? Maybe 1 kilohertz, 1000 hertz. So during that time, you if you think of, say, this is 10 hertz, this is 1000 hertz, so 100 times. So if you look at this Y, this one, right, it doesn't change. It doesn't change for, let's say, 1/10 of a second, because it's 10 hertz, right? Let's say this is a discrete version, not the continuous version. In the discrete version, Y doesn't change for 1/10 of a second. That's about 100 milliseconds, right? For 100 milliseconds, Y doesn't change. So let me draw it like that. This is 100 milliseconds, right? From here to here. Y doesn't change, right? This is 100 milliseconds or 0.1 seconds, right? So Y doesn't change. But if you look at Y hat, it changes, right? It changes 100 times within that 1.1 seconds. It changes 100 times. So therefore, initially maybe like this, then like this, 100 times. So it gets there quickly, and then there's a lot of time to spare, right? So this is y hat. So if you look at the big loop, right, after 0.1 seconds, when it comes up and look at the feedback, right, what you get from x hat is exactly x. It's exactly x, because by that time y hat is equal to y somewhere over here, right, and therefore x hat is equal to x. But if you look at the early stage, maybe this area, right, y hat is not equal to y. So therefore, right, we can say y hat is not equal to y, right, during that period, this period. So therefore, x hat is not equal to x. X hat is not equal to x. So if you feed back during that time, you are doing, you are not actually doing a good job. You are feeding back not the correct states, right? So if the observer-based controller to perform better, you've got to make sure that the observer plant operates 100 times faster than the main loop, right? So this is not practically possible if you implement it with software. Okay, is that clear? These are good questions. Yes. So others also, please raise your questions, right? Whenever you don't understand the concepts or anything related to the subject matter, right? That will help not only you, but others also. Any other questions, please? Right. We have a few more slides to go, I think. Yeah, we will take it next time. Yeah. So I just can't start this point because there's no stop nearby. Right. Okay. Then let's call the day off. I'll upload the lecture notes and the videos, right? Maybe today I can do that. Of course, you can start working on the deadbeat controller assignment, right? I will upload that also tonight. Right. That's it for the day then, and I'll see you next week. Have a good evening. Yeah.
Sir, the assignments, whether previous assignments were uploaded, we checked the Moodle, but this is going to be the first assignment, right?
This is the first assignment, yes.
Right, okay. Because
Yeah.
you said earlier that was assignments were submitted, uploaded, we checked, but yeah, okay, sir, right.
Yeah. Tonight, I'll do that.
Thank you, sir.
Thank you. I'll see you next time.